Howdy, and welcome back to my introductory astronomy lecture series, lecture 19, the universe of galaxies. Now, as you can see here, as I'm recording this from my home, we might have a visitor. This is Luna, and she likes to wander around while I'm at my desk because, well, she's a cat, and they do that. Occasionally, she will also jump down from a very high height to announce herself, and so it may look like I'm experiencing an earthquake, very much like that. So, if you'll forgive me for that, we can get started. And so as I said, the lecture today is going to be concerned with the universe of galaxies. Now, galaxies have been observed since really the mid-1800s, although they weren't recognized as such at the time. They were referred to as spiral nebulae. They appeared as, well, nebulous or blobby, I guess, structures that had, not star-like, that had spiral arm structure to them. There was even a claim that these spiral nebulae were actually rotating on fairly short timescales. Up until around the early turn of the century, thank you, Luna, turn of the century, there was a contention as to how large the universe was. And so the previous model by Kapteyn, was otherwise known as a cheese box model, was very small, and the Earth was at the center of it. Well, Harlow Shapley came along, and as I discussed in the last lecture, he used standard candles, in this case pulsating stars, to determine the to determine the distances to various parts within our galaxy. And he was the first to really map out the Milky Way galaxy, and he was the one who properly put us away from the center of the galaxy. Where he got things a little bit wrong, as it were, was the fact that he believed that the Milky Way galaxy, what he had mapped, was in fact the entirety of the universe. He believed that those spiral nebulae that we were seeing was in fact localized or local to our own environment, at least astronomically speaking. And so that began the great debate around the turn of the century between him and Abel Curtis. Curtis essentially took the complete opposite viewpoint. One, he disagreed that the Earth was not the center of the universe. He still put even though Shapley had made convincing observations to say that it was not, Curtis rejected those observations. But he also believed that the universe was far larger in extent than what Shapley was telling us. He believed that those spiral nebulae were in fact galaxies or island universes in and upon themselves. This argument didn't last very long, simply because around 1921, if I know my dates right, which I probably don't, somewhere in there, a gentleman by the name of Edwin Hubble made a groundbreaking discovery in that he noticed that not only were galaxies much farther away than Shapley had anticipated. We're talking, instead of the universe being hundreds of light years across, it is now millions of light years in size, at the very least. Because he was able to determine the distance to Andromeda to be about 2.5 million light years away. And he also, sorry about that, he also, probably the more groundbreaking consequence of his observations was that he noticed that the universe was in fact expanding. So not only was the universe far greater than we had previously thought, the universe was not steady state. It was not something that had existed for all time and would exist for all time, but it was in fact expanding outward, or I really should say expanding larger, to become larger. I'll explain why I chose those words differently in a later lecture when we talk about cosmology. But also the consequence was that the universe ultimately had a beginning. Now, I'm kind of getting away from the main thesis of this lecture, which is in fact just studying galaxies themselves, but I did want to place a framework, a historical framework, to really why galaxies, or how galaxies became a major field of, or major topic of study. Eventually I'll learn how to progress slides without having to look around. Anyway, so techniques for measuring distance. Ultimately, what we want to do is we go back to the very simple relationship which I talked about when I talked about light and spectra, and that is that light is decreases by the inverse square. And so there are three properties which are interrelated. There's the luminosity, or the intrinsic brightness of something. There is how bright that thing appears, and then there is the distance that thing is away from us. Now, for most measurement techniques, we are essentially attempting to in some way derive the absolute luminosity of an object, and then measure its apparent brightness, and then we can derive the distance. The major technique that doesn't require that is parallax, which I've just talked about, again, in a previous lecture. We're actually looking at the motion of a star as it moves backwards, or appears to move backwards and forwards, as the Earth orbits around the sun. But everything else, but most of the other ones, specifically when we talk about standard candles, those being pulsating variables and type 1a supernovae, what we're really doing is trying to find a proxy that gets us to the intrinsic brightness, or the absolute luminosity of an object, so that we can compare it to observational brightness and then backtrack to get to distance. Which brings us to something known as the cosmic distance ladder. Now, these are techniques which stack on top of each other, hence why they're referred to as a ladder. And what I mean by stack on top of each other is that one is calibrated onto another. And so the first real definitive distance technique that we use is actually radar finding. We are able to use radar pulses to find the distances to planets, to asteroids, and so forth within our own solar system. We then use the parallax method on those objects, and we determined that the radar finding and the parallax measurements gave us consistent results. And so we had confidence that trigonometric parallax, was a valid method for determining the distances. And for a long time, we were able to map out roughly about 300 light years or so using trigonometric parallax. Beyond there, we had to use other methods. We have since been able to enlarge that range with the Gaia telescope, the Gaia satellite, to actually be able to use trigonometric parallax to measure essentially the distances within our own within our own galaxy. But before then, we still needed other distance measures. And so again, I refer to the pulsating variables, specifically Cepheids, where Henrietta Leavitt was the one who determined that there is a period luminosity relationship. She was able to determine that the intrinsic brightness of an object was related to how quickly it pulsated. And again, there was an overlap. We were able to look at a subset of stars that were measurable by trigonometric parallax and the pulsating variable, or the pulsating variable technique, or the period luminosity relationship technique. And we found that they were, again, consistent. And so we could then say, all right, we can use this technique, this period luminosity relationship, for stars that could not be detected or could not be measured with trigonometric parallax. And then we go to the Tully-Fisher relationship, and then the type 1a supernovae, and then finally Hubble's law. Each of these I will go into a little bit of depth. My chair is really squeaky. And so this is going over the measurements of our galaxy. It is a bit dated, because as I said, with the advent of Gaia, we now are able to measure distances out to the edges of our own galaxy rather than maybe 300 light years or 100 parsecs away from us. Prior to that advent, we actually used another form of parallax, although honestly I don't know why the two have the same name, because I can't really see the connection to them. But this is an intermediate rung between trigonometric parallax and Cepheids, or pulsating variables. And the idea here is we can use spectra to determine the bulk characteristics of a star, one of which is luminosity. And as I said, if you know the luminosity, then you can measure the apparent brightness and you can get the distance from that. Spectroscopic parallax is pretty good. It's out to about 10,000 light years or so. But really, the main workhorse method was, in fact, using standard candles. The first standard candles that were used were Cepheid, or were recognized as such, were the Cepheid variables. Again, that was Miss Leavitt's observations. But Harlow-Shapley actually used another type, RR Lyra's, within globular clusters in order to measure the distances out to the extreme ends of our galaxy. There are a number of different pulsating variables, and so we can use them, use pretty much any of them. Oddly enough, oh, that was Sunny, my other cat. And yes, I'm an astronomer who has two cats. One is Luna and one is Sunny. Yeah, I am a walking stereotype. Anyway, Harlow-Shapley, again, the master of using pulsating variables to determine distances, and the one who basically claimed that the universe was, the Milky Way galaxy was the entirety of the universe. I find it a little bit ironic, as it were, that Edwin Hubble essentially used Shapley's technique to prove him wrong. He used Cepheid variables within the Andromeda galaxy to determine that the Andromeda galaxy was millions of light years away. And Cepheids have pulsating variables, really have an effective distance of a few tens of millions of parsecs, or tens of millions of light years away. And so it gets a fair extent out to the universe, and we can use these standard candles to measure or to map out our local galactic environment. But if we want to look at anything beyond that, if we want to start looking at the galaxies, really what galaxies looked like in the intermediate past, then we have to use something like the Tully-Fisher relationship. Tully-Fisher relationship, the first order, is pretty straightforward. It's very simple. Essentially, the faster a galaxy rotates, the more mass that it has. Now, I'm putting aside the dark matter quotient, although it is fairly related to it. Essentially, again, the idea is very simple. If you have more mass, then the acceleration felt by that by gravity is going to be larger, and if you have a larger acceleration, you have a larger velocity. And so it's as simple as that. The larger, the more mass that a galaxy has, the faster it's going to rotate, because the more gravity, the gravitational potential is much higher in these. Now, there is what we refer to as a selection effect, which is that this technique is only viable on basically a subset of galaxies, because of the way that the technique is used. In order to determine the velocity, basically how fast something is rotating, we are limited to essentially spirals, because as I'll mention in a moment, other types of galaxies do not have as regular motions or regular rotation to them. So we have to use spiral galaxies, and in order to get an accurate, a more precise measure of this, I should say, a precise enough measure that we can actually utilize this law, you need to worry about edge-on spirals. Edge-on spiral. The galaxy that's on the screen with the Andromeda Galaxy, that would be close to an edge-on spiral. It's basically if we're looking at the dinner plate from the edge, or basically from the table's perspective. Face-on is if we're looking above the table down onto the dinner plate. And so this is a representation, just a simple representation of what the Tully-Fisher law states. Again, a smaller galaxy, a less massive galaxy, is going to rotate slower than a larger galaxy. And this is essentially a linear relationship between the two. There is, I would be remiss in saying this, there is a corresponding or an analogous law for elliptical galaxies. Essentially, we look at the velocity dispersion. We look at the differences of the speeds of stars within that galaxy. But in principle, it's the same idea. The mass of the galaxy dictates how fast things move. If you have a larger mass, or if you have a larger velocity, then you have a larger mass. Now, how does this get you distance? This gets you distance because you can use the mass to then infer how luminous this galaxy is. And again, luminosity plus apparent brightness gets you distance. And then we come to the Hubble law. Now, the Hubble law, as dictated by Edwin Hubble, what he did was that he combined observations of Cepheid variables in galaxies, and he was able to get the distances to those galaxies using the Cepheids. He then tied that data to pre-existing velocity data, pre-existing data taken of these galaxies, where the redshift was determined. Just as a reminder, redshift means that as a star or an object is moving away from us, because of the Doppler effect, that object is going to appear slightly redder than it would if it were sitting still. And so he's using these Doppler measurements tied to his own measurements of distance, and he determined something rather spectacular. He determined that the universe, as I said, was A, much larger than we had anticipated, and two, he noticed that the galaxy was in fact expanding. Now here's essentially the mathematical relationship of redshift, where the velocity of an object, in this case the galaxy, is equal to one of the, really any, but a particular wavelength, absorption wavelength that we observe, minus that wavelength as observed in the lab, divided by that lab wavelength times the speed of light. And so he came up with basically this sort of data. His initial data was not nearly as pretty as this, and it didn't have nearly as many components, but ultimately, with further study, we get data that resembles what you see on this slide, which is very simple. You have the recessional speed, or the velocity of the galaxy moving away from us, as a function of distance. And he noticed that when he plotted that up, that the farther something is, or the more distant a galaxy is, the faster it's going away from us. And what was astonishing is that, very much like the Michelson-Morley experiment, which determined that the speed of light was invariant no matter where you looked in the universe, so is this, in a sense, that everything, at least on larger scales, all of the galaxies appear to be moving away from us. Really, the best explanation for how that is, or why that is that the universe seems to be expanding from our position. Later on, we're going to talk about we're going to revisit the cosmological principle when we talk about cosmology, and we're going to realize that this effect, this expansion from us, is not unique. If we were to go to the Andromeda Galaxy and reproduce these observations, we would see that the universe was expanding from the Andromeda Galaxy. If you go to M87, for example, again, it would appear as if all things are expanding away from M87. But that's a topic for a different lecture. The Hubble law is, again, one of those simple laws that are so foundational and so just powerful in physics and astronomy. I like to harken back to this point. F equals ma, E equals mc squared. Now we have V equals hd. These are fundamental, just groundbreaking equations that are exceedingly simple. And it just amazes me that nature works in this way. Hubble law, like I said, is the velocity of a galaxy is equal to a constant value times, let me restate that. The velocity of a galaxy is equal to a constant value, now known as the Hubble constant, times the distance. So easy peasy. If you know your physics, or at least your introductory physics, you can probably guess or see that the Hubble constant is related to time. And we can use the Hubble constant to make an estimate of just how long the universe has been around. So when we talk about the age of the universe being 13.7 billion years old, we're really talking about an estimation of, or that estimation stems from the Hubble constant. And right now we believe that the Hubble constant is 69 kilometers per second per megaparsec, which is a really, really cumbersome unit, but there it is. The one thing I will say about the Hubble constant is that this is, again, something that we did not know very well until very, very recently, until within the 2000s. When I was coming up as a grad student, the error, or the range, that's the word, the range of the Hubble constant was between 50 to 100. So we really did not know the age of the universe very well. It was only until more recently that we were able to determine that. Now let's talk about galaxies. Let's get into the actual meat of this lecture. This is what is known as the Hubble tuning fork diagram. Now I want to emphasize, or truly emphasize, this is not an evolutionary sequence. Galaxies do not start on one end and then progress over time to the other. I don't know why Hubble decided to create this tuning fork diagram, but it is what we have today. But it separates the galaxies into three major categories. You have elliptical galaxies, you have spiral galaxies, and then you have irregular galaxies. And because astronomers aren't the most creative or original folks in the universe, you probably guess why they're called that. Elliptical galaxies are elliptical in shape. Spiral galaxies have spiral arms which wrap around or emanate from the center, and irregular galaxies don't have any consistent shapes whatsoever. You cannot find two irregular galaxies that essentially look the same. There is a subcategory of spirals, and that is what we refer to as barred spirals, hence the tuning fork. The upper are normal spiral, quote unquote, normal spirals. The bottom ones are quote unquote barred spirals. Not going to really get into why there is, what the mechanisms behind, what forms a bar and what doesn't. It's beyond the scope of this course. Just realize that spirals can essentially come in two different flavors. Incidentally enough, the Milky Way galaxy, unlike the Andromeda galaxy, which is often used as a proxy for our own, the Milky Way galaxy is believed to have a bar in its center, or coming off of its bulge, whereas the Andromeda galaxy does not. And I would be remiss in describing what an actual bar is. A bar is a linear distribution of stars emanating from the bulge, and from there, the spiral arms come away. We can then even subcategorize these galaxies. So if we take the ellipticals, we subcategorize them based on their ellipticity, or just how elliptical they are. You go from E0, which is essentially an ellipticity of 0, and it looks like a soccer ball. You go to longer, or higher numbers, the ellipticity gets greater. So an ellipticity of 3, you have something that looks like a rugby ball. You have an E6 that looks more like a cigar. With spirals, we can subcategorize them based on their bulge size and the windiness, technical term, of their arms. So an SA galaxy, A subclass, has a large bulge and tightly wound spiral arms. B has a smaller bulge and less wound, and then C has a very small bulge, or comparatively small bulge, and very loosely wrapped spiral arms. And then you have SBA for barred spirals, and so forth. There is one sort of peculiar galaxy that is sort of an intermediate stage, and this is where some folks were thinking that it might be an evolutionary sequence, which it's not, is at S0s, or lenticular galaxies. These are galaxies that are disk-like. They have a bulge, they have a disk, but they don't have any spiral arm structure within them for one reason or another. And so when we look at the overall overall characteristics of these galaxies, we see, again, as I described with the Milky Way galaxy, you have a disk component, you have a bulge component, and you have spiral arms and potentially a bar within the central region. Elliptical galaxies are triaxial in shape, and really what that means is that think of it in 3 dimensions. It's got an x-axis, a length, a width, and a height. Now, with elliptical galaxies, 2 of those arms are almost always going to be equal. So it's either going to look like a cigar, or it's going to look like basically a plate without really a bulge sort of situation, or it's going to look like a ball, like a soccer ball. Irregular galaxies really have, again, as the name would imply, there is no simple geometry. There is no way to really classify them as per their shape. When we talk about stellar orbits, I should also say that elliptical galaxies also do have an extended halo. There is a larger distribution of globular clusters surrounding ellipticals, very much like with spirals. With spiral galaxies, when we talk about the disk, we're talking about very ordered systems in the sense that the stars orbit around in a prograde way. Counterclockwise when viewed from the north, the eccentricities are fairly low, the inclinations are fairly low, they're all fairly constrained within the disk. In the bulge, it gets a little bit more disordered. The inclination spread or range is a little bit higher. The eccentricities can range to be a little bit larger. And then in the halo, it's basically all bets are off. Much larger range in eccentricities and inclinations. With ellipticals you can think of as just much larger bulges. The orbits are far more random in ellipticals than they are in spirals. While there is I don't know if I would say that. Instead of looking at the rotation of a spiral galaxy, in ellipticals we look at the velocity dispersion, the differences between slow-moving stars and high-moving stars, or the velocities of the slowest moving stars and the velocities of highest moving stars. That is dictated by how much mass is there, and then, like I was saying, with the Tully-Fisher relationship, there is an analogous there. With irregular galaxies, again, fully randomized orbits. With elliptical galaxies, they are somewhat constrained in the fact that they are elliptical in shape, where 2 arms are approximately equal to each other, and one arm is either much longer or much shorter than the other 2. With elliptical galaxies, or with irregular galaxies, that's not the case. Basically, the orbits can be all over the place. Size ranges. Spiral galaxies tend to be between big and huge. Big meaning that there is about 5,000 parsecs across, or 100,000 parsecs across. There are no what we refer to as dwarf spiral galaxies. We do not see spiral galaxies on a much smaller scale. So when we talked about the local group, I talked about 3 major galaxies, the Milky Way, the Andromeda, and the Triangulum, and then 24 or so smaller galaxies orbiting around all of those. None of those smaller satellite galaxies are spirals. We do not believe that a spiral galaxy can form that. A galaxy that small cannot form into a spiral. We have no evidence of that. Now, ellipticals can get as large or even larger than spirals, and they can also be smaller. So with dwarf ellipticals, we're talking about things on the order of maybe hundreds, if not thousands thousands of parsecs across. And then you have giants that are hundreds of light years across. These are some of these are what we refer to as SD ellipticals, or cluster dominant ellipticals. And then irregulars are on the low end of the spectrum. So they can be anywhere between dwarfs. So there are dwarf irregulars, and then there are some irregular galaxies that are on the size scales of the lower spirals and the mid ellipticals. So to reiterate, spirals go from big to huge. Ellipticals go from tiny to ginormous. Irregulars go from tiny to big. All of these galaxies are believed to have dark matter halos. We have evidence to suggest that dark matter exists in these galaxies and is distributed in the same way, in a roughly homogeneous spherical distribution around these galaxies. When we look at the prevalence of galaxies, this may in fact be a selection effect, in the sense that spiral galaxies tend to be most common. Elliptical galaxies are less common, but still fairly common. And then irregular galaxies are the least common. Now, the reason why I say this might be a selection effect is there does seem to be a physical reason why there would be more spirals than ellipticals, but the irregular galaxies may simply be less common because we just can't see them. As I mentioned before, one of the arguments for dark matter is massive objects that are very, very dim. Now, an irregular galaxy doesn't really fit this description so much, but it is possible that there are irregular galaxies out there that are just dim enough that we cannot observe them with any kind of, what's the word I'm looking for? We're just not picking them up. So they are few in number because we are only seeing the brightest of those irregular galaxies, or the closest of those irregular galaxies. Now let's turn our eye to star formation. Star formation is very prevalent in spiral galaxies, particularly in the spiral arms. That spiral density wave that I talked about in the last lecture basically compresses the gas within the disk, and as the gas compresses, gravity is enhanced, and that basically starts star formation. Elliptical galaxies, and I'm probably going to say this quite a bit, are what we refer to as red and dead. They are older. They have much older stars, which are redder and redder because all the bluer stars have long since died off. And there is no active star formation within these galaxies. While there may be dust lanes, there may be material from which stars can form, it is not in a compact nature. It's not trapped within molecular clouds. And ellipticals are almost devoid of gas, definitely comparatively speaking to spirals or irregulars. In some cases, irregular galaxies have a tremendous amount of star formation. In other cases, not so much. And common phrase for mine. We'll get into that later on, and we'll explain why that is the case. And it's tied to the most likely explanation for why irregular galaxies form the way they did. With stellar populations, as I said, ellipticals are red and dead. They are a much older population. All of the blue stars have long since died off, leaving behind either evolved red giants or orange or red main sequence stars. Spiral galaxies run the gamut. We have red stars, basically fairly old red stars, all the way up to fairly new blue stars. Because star formation is still an active, ongoing process, these shorter-lived blue stars are still being manufactured, which is why when you look at spiral galaxies, depending on what's going on, those spiral galaxies will tend to be bluer in color than the ellipticals, because these blue stars are the brightest component when you look at the distribution of brightness of all the stars. Irregular galaxies, as one would expect, would have a younger population and a bluer population if we see that star formation is active. If it isn't, then they're going to be more like ellipticals. The population is going to be more on the older side. The colors are going to be on the redder side. Now, in terms of supermassive black holes, again, we hypothesize, and this is more of a hypothesis than an actual. For spirals and ellipticals, we have very solid evidence that there are supermassive black holes in these galaxies, to the point that we can confidently state that any elliptical or spiral galaxy is going to have a supermassive black hole within its center. Irregular galaxies, maybe. Depends on the size. One of the open questions that we have for supermassive black holes is that we know there are black holes that are about the size of the sun, or tens of times as mass of the sun, and we know that there are black holes that are millions, if not billions, of times mass of the sun. But when it comes to smaller galaxies, like irregular galaxies or dwarf galaxies, we would anticipate that those would have, if they have supermassive black holes in their cores or their centers, those those black holes would be on the order of hundreds of thousands of solar masses, or possibly thousands of solar masses. These are what we refer to as intermediate mass black holes. We have not observationally detected those. We have not been able to find those. Again, that may be a selection effect. Because these objects are so much smaller, their effect on the surroundings is also going to be commensurately smaller, and so that we may not have the technology to be able to detect that influence. But that is, like I said, it's still an ongoing active form of research. Now, a couple of different properties of spiral galaxies is we have what we refer to as grand design spirals, which you can see on the bottom, which you have a clearly defined spiral structure to it, or you can have flocculent spiral galaxies, which sounds a little rude, but these are galaxies like you see on the top, where the spiral arms are hinted at, but because they do not have a definitive shape, the arms are broken into pieces, and so you can sort of trace out where the arms would most likely be, but they're not as clearly defined as they are in the grand designs. Here's an example of a very barred spiral, which you can see again, this bar emanates from left and right, in this case, from the bulge in a very linear fashion, a very straight line fashion. It goes out to some distance, and then the spiral arms emanate off of that. This is the triaxial nature that I was talking about. Here we have the axes instead of X, Y, and Z. You have A, B, and C. In this case, B and C are reasonably close together, and A is not. Or at least A is significantly larger than B and C. And as also I mentioned before, these ellipticals have extended halos. These are similar to the halos of spiral galaxies in that they contain globular clusters. They also contain very high temperature gas, high temperature, low density gas. Which brings us to irregulars and lenticular galaxies. Again, lenticular galaxies are galaxies that have a significant bulge, but do not have a significant bulge without a comparatively substantial disk, and they certainly do not have a spiral arm structure, and do have characteristics reminiscent of both ellipticals and spirals. And then you have the irregular galaxies. Large and small Magellanic Clouds are the best examples of those we have. They are the ones pictured. Large is up, small is down. These are these are the biggest satellite galaxies to the Milky Way galaxy. As you can see, they are fairly blue in color and irregular in shape. In the last lecture, I talked about dark matter. Dark matter is matter which is dark for one reason or another. And what I mean by dark is that we do not readily observe it when we look at a galaxy. The evidence, not the first evidence, but the sort of the evidence that got everyone up on their feet saying, oh, maybe this is really a thing, was looking at rotation curves of galaxies. We found it first with our own galaxy, and then we found that this phenomenon occurred in pretty much every other galaxy we looked at, or at least spiral galaxy that we looked at. And this phenomenon is that when we look at the rotation speeds within the disk, so in all of these cases, you have basically a linear rise in velocity as a function of distance. That's basically what's happening within the bulge. And then after you get out of the bulge into the disk, while we would expect the velocities to drop off with distance, as Kepler's law would tell us, what we actually observe is that the velocities stay relatively constant across the distance. And what that indicates is there must be an extended source of mass which is relatively evenly distributed across the entire galaxy. So dark matter is let me rephrase, or try again. There is what we know, or what this data tells us, is that there is matter there that we cannot see. What that matter is, again, is open to debate. I talked about massive and dim normal matter. Essentially, these are planets, white dwarfs, things that we just can't see because we don't have the technology to do so, or the sensitivity to do so. Or this dark matter could be exotic, or more exotic. It could be neutrinos, or axions, or things of that nature. Again, still very much of an open question. Now let's talk about the evolution of galaxies. Now, galaxies in and upon themselves will, if left to their own devices, what would essentially happen is that they would keep their own shape, or we believe they would keep their own shape, and ultimately they would use up their gas and dust and ultimately become red and dead. So spirals can become red and dead. Well, as it happens, as I again mentioned in the last video, there is a thing called galactic cannibalism. The distances between galaxies, that is the size of the galaxy, or at least the size of the gravitational influence of a galaxy, is large in comparison to the distances between them, which means that mergers or interactions between galaxies is far more likely than, say, stars interacting with each other. And because these galaxies are so large in their distributions, it's not a simple factor of two globs morphing into each other. When these two galaxies interact with each other, it becomes a mess, as you can see from these images. They go through a rather chaotic phase and then end up in a final stage. Now, what we found is that when you start off with two galaxies, it doesn't matter what kind they are, two irregulars, two spirals, two ellipticals, an elliptical and a spiral, you get the idea. Anything you start off with, when you smash them together, you're going to get an elliptical at the back end. And that elliptical is going to be roughly the combined mass of the two stars. There is going to be some mass loss due to basically gravitationally slingshots, but it's going to be comparatively much larger than the two other galaxies. Depending on when you look at these galaxies, that's going to, particularly if you look at example C, or E, or F, really, the galaxy is going to appear irregular. Now, that's essentially where we believe irregular galaxies stem from, is that an irregular galaxy is an example of some kind of galactic either merger or interaction. Either the two galaxies have eaten each other, or a galaxy has come by another galaxy and just basically ripped it apart and left it alone. So galaxy evolution is kind of a question um, well, I was going to say of age, but that's sort of obvious. So what I'm trying to say, coming back around, is that you have elliptical galaxies are some of the oldest galaxies, oldest and newest galaxies that we have. Essentially, what I'm trying to say badly is that you have elliptical galaxies that formed initially in the early parts of the universe, and then we have galaxies that form much later due to these mergers. And we see some of the largest elliptical galaxies in the centers of dense clusters of galaxies. And like I said, these are called CD, or cluster dominant galaxies. There's a lot of multiple galaxy mergers within that cluster, and it has become a large elliptical. That large mass concentration has basically shaped the cluster of galaxies around it. Now let's talk about active galactic nuclei, or AGN. Now, AGN is sort of, when I talk about AGN, I use the term loosely, in that I'll either use AGN to describe as a name for the galaxy, or as the name of the engine within that galaxy. In AGN specifically, if I'm going to be precise about my definition, AGN is actually the engine within the galaxy itself. So you have a normal spiral galaxy, for example, and inside that spiral galaxy you have an AGN. So, but intentionally, sometimes I get lazy and I'll just call the whole thing an AGN. AGNs are distinguishable because they are very small in size. They're exceedingly high in luminosity. In some cases, the luminosity of the AGN, of that small engine, and we're talking about something on the order of solar system size, or possibly a little bit, about 1,000 light years or so. Excuse me, a light year, not 1,000 light years. A light year. A very small object. It's producing more energy than the entire rest of the galaxy combined. You have strong emission lines in both the continuous, you have strong emission in the continuous spectrum, meaning that you have, again, tied to luminosity, you have a lot of emission coming out of that region, and you have strong emission lines, meaning that there is a lot of lower temperature gas hanging out around the active galactic nuclei. They're also variable across multiple wave bands. You have, and what I mean by variable is that the luminosity of these things, or the apparent brightness of these things, changes sometimes exceedingly rapidly, like on the millisecond range, all the way up to hours to days, or even longer. And what we have, the AGNs can be subcategorized into a variety of different ways. You have Seyferts, you have radio galaxies. We'll next talk about quasars and blazars, and then there are a slew of others that we could talk about. Seyfert galaxies they have, again, relatively rapid changes in brightness, and they have broad emission lines from very highly ionized gas. And the broad emission lines tell us that the inner part of the AGN itself is rotating very, very rapidly because the line gets broadened out by the Doppler effect. Radio galaxies are galaxies that are, while AGN are loud across the entire board, across the entire electromagnetic spectrum. Some galaxies, so that means that all of them have a higher than normal, as it were, radio spectrum. Some galaxies, or some AGN, actually have even louder, which are referred to as radio loud or radio galaxies. And when we look at these, we notice that these are large, high temperature lobes or jets of gas that come out from either side of the central region, the central AGN. Then we have blazars and quasars. Quasars were actually the first AGN ever discovered, and they are, the quasar is an acronym which stands for quasi-stellar radio source. These were, again, very loud radio objects, and when we looked at them, when we looked at the spectrum of them, we noticed that they are exceedingly high in redshift. So the reason why they're stellar and they're quasi-stellar is that they were not extended objects. They didn't really look like galaxies, but they were just impossibly bright and moving away from us at very, very high rates of speed. And so these are significantly large objects, but because they're so far away, they look more star-like. Blazars are things that are very, very variable. And when we look at them, like I said, these are the ones that are variable on order of milliseconds, seconds, minutes, and so forth. And their variability is very irregular. It's not periodic in any way. When we look at the AGNs, what we find when we look at the characteristics of them, we have been able to understand that all of these different classifications are really just changes in the perspective. I was, in my department, I was part of in my department there was a group, an AGN group, a group of professors who studied AGN. And every time there was an AGN talk, colloquium seminar, what have you, they would show a diagram, something like this, which we affectionately known as the exploding donut. And what this shows us is essentially the model behind what we expect or what we believe an AGN looks like. What you have is a supermassive black hole at the center. You have an accretion disk around that, which is what's generating the tremendous amount of energy that we detect. There are these jets that stream off from the poles of the black hole because we're talking about an exceedingly high magnetic field. And so that produces jets. We've talked about that in terms of protostars. We've talked about that in terms of stellar of neutron stars, black holes, and a few other objects. You have these very powerful, very, very energetic jets that are that shoot out in a very column. Surrounding that, you have large dust cloud or dust and gas clouds, which are orbiting around at high rates of speed. And then surrounding that, you have a torus of material, primarily composed of dust. And so when we look at these AGN, it very much depends on how we look at them as to how we define them. So, for example, the blazars are very bright but very variable because we're looking on the throat of that black hole. We're looking down the jet, which is very erratic. The material within that jet is very erratic. It's moving around. It's very sort of I'm looking for spotty. Chunky. It's very chunky. So there are a lot of different discrete chunks that move very, very quickly, nearly relativistically, or sometimes relativistically within that jet. Quasar is if you're looking at it just slightly off center, you're not seeing that blazar, so you're not seeing quite that much variability, but you're pretty much looking directly at the disk, and that's where the majority of the energy is being generated within that AGN. Cepheid 1s, we'll just talk about Cepheids or Cepheids. Cepheids, you're looking off at an angle, and so not only are you able to see the engine, the black hole, and the accretion disk, the energy being generated there, but you're also having a fairly good look at those those gas clouds which are moving around at very high velocities. Those explain the broad lines that we see. So, why do we have supermassive black holes? Why do we believe that there are supermassive black holes? Ultimately speaking, it's simply because of the amount of energy that it's generating. The energy is being generated by, again, that accretion disk. As I mentioned in the last lecture, when or hopefully I mentioned in the last lecture. Anyway, I know I spoke about it when we were talking about X-ray binaries and white dwarfs. When you have an accretion disk, it obeys Keplerian rotation, meaning that the inner part of the disk is going to rotate faster than the outer part of the disk. And what that sets up is shearing. The best way of looking at it is sort of a frictional effect. The inner part of the disk is moving faster, and so it's going to rub up against the layer right on the outside of it, and that friction is going, or that shearing is going to generate a certain amount of energy. And that energy is dependent on is directly related to the velocity differences between the two layers. When you get to the inner part of the disk, the velocity difference is larger, so you get more energy in the or energy generated at higher frequencies. All the photons that are created are of higher energy. As you get to further away, lower they go. So if we're talking about, for instance, a planetary nebula, or excuse me, a protoplanetary disk, the edges of the disk, you're going to get radio and maybe far infrared, all the way up to sort of the mid-infrared, near infrared part in the inner part of the disk. When you talk about white dwarfs, you go from radio all the way up to, say, UV, because the area that the disk basically can, the hole in the disk is smaller. So for a protostar, the protostar is going to have a radius of approximately 3 times the radius of the sun. And so that's going to basically carve out a certain size hole within that disk. But if that object is smaller, like a white dwarf, for example, that that hole that is carved out gets smaller, and subsequently you can have regions of a disk that are shearing against each other with such speed that you generate UV light. And you can keep going along with that analogy until you get to a supermassive black hole, where you are now getting energy being generated not only in the ultraviolet but also in the X-ray and some in the gamma ray itself. The only thing that the best explanation that we have for what could potentially be generating that much energy over that over that large range of wavelengths is a accretion disk surrounding something that has a spatial size that is very, very small, but has a tremendous amount of mass, a mass that is needed to move this disk as rapidly as it does to generate those energies that we have detected. It also explains the powerful jets that we see that, again, move material at near relativistic speeds. All right. Well, that's where I'm going to end this lecture, and again, I hope you have found it informative, if not enjoyable. And the next lecture we talk about will be on large-scale structure of the universe. We're going to move away from looking at galaxies, and now we're going to be looking at groupings of galaxies and how those groupings of galaxies allow us to understand how the universe may have formed. All right. Hope you enjoy the rest of your day, night, whatever. Peace out.